October 2012. Headlines everywhere. Scientists discover planet made of diamond. Super Earth worth $26 non-million found. The Bling Planet. Astronomers find cosmic treasure. It went viral instantly. Mining companies got calls from investors. Science fiction writers started novels. Jewelers made jokes. The planet. 55 Cancri E, 40 light-years away. Twice Earth size. 8 times the mass. And according to models, a mantle made of diamond. An entire world of crystallized carbon. Fast forward to 2024. The James Webb Space Telescope looks at 55 Cancri E. What it finds? Not diamond, an atmosphere, volcanic outgassing, possibly a magma ocean. The Diamond Planet isn't a diamond planet. So were scientists lying in 2012? No, they were doing something much more interesting, making educated guesses with limited data, then refining those guesses when better data arrived. This is a story about how we know what we know. About 40 light-years away, a distance so vast light takes 40 years to reach us, there's a planet we've never visited, never touched, never directly photographed. Yet we claim to know what it's made of. How do we figure out the composition of worlds we can't reach? Why do headlines get it wrong? And what does this tell us about reading science news? The real story is better than the diamond myth. Let's investigate. First, understand the target. 55 Cancri is a binary star system, 2 stars orbiting each other. The primary star, 55 Cancri A, is slightly smaller and cooler than our Sun. It's in the constellation Cancer, 40 light-years from Earth. Visible to the naked eye on a dark night. You've probably looked at it without knowing. Discovery, 2004. Radial velocity method detected it first, watching the star wobble as the planet's gravity tugs on it. Confirmation, 2011. Transit observations. The planet passes in front of its star, blocking a tiny fraction of light. From these observations, we learned orbital period, 17.7 hours, less than 1 Earth day. Distance from star, 0.016 AU. That's 1/60,000th Mercury's distance from the Sun. Surface temperature, approximately 2,400 Kelvin, 2,127 degrees Celsius, 3,860 degrees Fahrenheit. Hot enough to melt iron. From transit timing and radial velocity measurements, astronomers calculated mass approximately 8.6 Earth masses, radius approximately 2.0 Earth radii, density approximately 5.5 grams per cubic centimeter. Now here's where it gets interesting. That density is similar to Earth's, but density alone doesn't tell you composition. A planet that dense could be rocky like Earth, silicates, iron core, water-rich under extreme pressure, carbon-rich, graphite, diamond structures. To narrow it down, astronomers looked at the host star. Planets form from the same material as their star. The star's chemistry hints at planetary composition. 55 Cancri A's spectrum showed something unusual. Carbon to oxygen ratio, higher than the Sun's. More carbon relative to oxygen. Why this matters? In planet formation, oxygen loves binding with carbon to form carbon monoxide, CO. Any leftover element determines what minerals form. High oxygen, like our solar system, leftover oxygen binds with silicon, forming silicates, rocky planets like Earth. High carbon, like 55 Cancri. Leftover carbon could form carbides, graphite, and, under pressure, diamond. This was the basis for the Diamond Planet hypothesis. In 2012, Niku Madhusudan, Yale University, and colleagues published models suggesting if 55 Cancri E formed in a carbon-rich environment, its interior structure might be surface, graphite or carbides, mantle, diamond, carbon under immense pressure, core, iron-carbon alloy, or even more exotic carbon phases. At the pressures and temperatures in 55 Cancri E's interior, carbon would crystallize into diamond structures. Not gem-quality jewelry, not transparent, but diamond, carbon atoms in a crystal lattice. The paper was careful. It presented this as one possible model given the data. The headlines were not careful. What the paper said. Carbon-rich planet models are consistent with the observed mass and radius. What the headline said. Scientists discover Diamond Planet. Within 48 hours. Google searches for Diamond Planet. 100,000% increase. News coverage. Every major outlet. Social media shares. Millions. Why did it go viral? Wealth fantasy. 26 nonillion valuation, calculated by multiplying mass by Earth diamond prices. Uniqueness. First of its kind. Visual appeal. Sparkling planet renderings. Simplicity. Easy concept. Planet made of diamond. Here's what happens when science goes viral for the wrong reasons. The original paper gets cited everywhere, often without context. Follow-up studies either confirm the possibility, get less attention, question the model, ignored by media. For 12 years, Diamond Planet became 55 Cancri E's identity. Meanwhile, astronomers kept collecting data. And the picture started to change. December 2025. The James Webb Space Telescope, JWST, turns its infrared eye toward 55 Cancri E. Why JWST matters? It sees in infrared heat radiation, perfect for studying ultra-hot exoplanets. The technique: secondary eclipse observation. When the planet passes behind the star, we lose the planet's thermal emission. By comparing brightness before and after, we measure how much infrared light the planet emits. This tells us surface temperature distribution, atmospheric composition, heat circulation patterns. For 55 Cancri E, JWST observed multiple secondary eclipses. What it found surprised everyone. Finding number 1. Temperature variation. The planet's day side is approximately 2,400 Kelvin, but there's a temperature gradient, not uniform heating. If 55 Cancri E were a bare rock, like the diamond model suggested, tidal locking would create extreme temperature differences, scorching day side, frozen night side. Instead, evidence of heat redistribution. Something is moving heat around. Finding number 2. Spectroscopic signatures. JWST detected atmospheric absorption features consistent with carbon dioxide, CO2, carbon monoxide, CO, possibly sulfur dioxide, SO2. These gases suggest volcanic outgassing. Finding number 3. Thermal emission variability. The planet's brightness changes slightly between observations. This suggests active surface processes, Possibly volcanic eruptions, magma flows, or atmospheric weather. The new picture. 55 Cancri E isn't a solid diamond world. It's more like a lava planet with a thin, dynamic atmosphere constantly replenished by volcanic activity. Current best hypothesis. 55 Cancri E has a global magma ocean. Why? Tidal heating. The planet orbits so close to its star that tidal forces, gravitational stretching and squeezing, generate internal heat. Like Jupiter's moon Io, the most volcanically active body in our solar system, but on a planetary scale. Possible structure. Surface. Molten rock, temperatures high enough to vaporize rock. Atmosphere. Thin. Made of vaporized rock, silicates, and volcanic gases. Interior. Still uncertain. Could be rocky. Could have carbon-rich layers, but not solid diamond. The carbon-rich chemistry might still play a role in the interior, but the surface dynamics are dominated by extreme heat and volcanism. So why did the diamond model fail? Issue number 1. Atmospheric evidence contradicts solid diamond mantle. If the mantle were solid diamond, the extreme surface heat should crack and sublimate surface layers. We'd see carbon vapor signatures. We don't. Issue number 2. Temperature distribution. A solid diamond mantle would have extremely high thermal conductivity. Heat would spread efficiently, creating more uniform temperatures. The observed temperature patterns suggest molten, convecting material. Issue number 3. Volcanic activity. Active volcanism requires molten rock reaching the surface. A thick diamond mantle would insulate the interior, preventing this. The 2012 model wasn't wrong in the sense of being unscientific. It was a legitimate hypothesis based on limited data. But when better data arrived, the hypothesis didn't hold up. This is exactly how science is supposed to work. Step back. Appreciate the challenge. 55 Cancri E is 40 light-years away. That's 378 trillion kilometers, 235 trillion miles. We've never been there, never touched it, never taken a direct photograph that shows surface details. Everything we know comes from indirect observations. 1. Transit photometry. Measuring how much starlight the planet blocks. Tells us radius, size. 2. Radial velocity. Measuring how the planet's gravity makes the star wobble. Tells us mass. 3. Transit spectroscopy. Analyzing starlight filtered through the planet's atmosphere during transit. Tells us atmospheric composition. 4. Thermal emission. Measuring infrared light from the planet's surface, atmosphere. Tells us temperature, heat distribution, atmospheric dynamics. From these puzzle pieces we infer composition. Here's the truth about exoplanet composition claims. They're educated guesses. Mass and radius can fit multiple composition models. Example: a planet with 8 Earth masses and 2 Earth radii could be rocky with a thick atmosphere, rocky with a water layer, carbon-rich with different interior structure, mix of all 3. To narrow down, we use host star chemistry, like the carbon-to-oxygen ratio, atmospheric spectroscopy, what gases are present, thermal properties, how heat moves, statistical comparisons, how similar planets behave. But even with all that data, we're still making models. Models that improve as technology improves. 55 Cancri E went from diamond planet to lava planet, not because scientists were wrong, but because we got better tools. Let's talk about how Diamond Planet became truth. Step 1. The science. Researchers publish, carbon-rich models are consistent with observations, pending further data. Keywords: consistent with, models, pending further data. Translation: this is one possibility. We need more evidence. Step 2. The press release. University PR writes, astronomers propose diamond-rich super-Earth. Hedging words disappear. Propose softens to implication of discovery. Step 3. The media. Journalists write, scientists discover Diamond Planet. Propose becomes discover. Uncertainty evaporates. Clickability maximized. Step 4. Social media users share. OMG, a planet made of diamonds! Nuance completely gone. It's a game of telephone. Each step removes qualifiers, adds certainty, increases virality. Why does this happen? Scientists need citations, funding, prestige. Exciting claims get attention. Universities need donors, applicants, reputation. PR departments amplify exciting research. Media outlets need clicks, views, ad revenue. Diamond Planet gets more clicks than carbon-rich model proposed. Social media algorithms reward engagement. Outrage and wonder beat accuracy. Nobody's actively lying, but the system amplifies certainty and buries uncertainty. When corrections come, when JWST data challenges the Diamond model, who covers it? The original story got 10,000 headlines. The update gets 50. This is the problem with science communication in the viral age. How do you separate hype from reality? Red flag number 1. Scientists discover. That are framing. Scientists propose. Data suggests. Models indicate. True discoveries are rare. Most science is incremental progress. Red flag number 2. Revolutionary claims without caveats. Real science is full of, however, pending, further research needed. If an article presents zero uncertainty, be skeptical. Red flag number 3. Single study definitive claims. Science requires replication. One paper is a starting point, not an ending point. Red flag number 4. Exact numbers for uncertain things. $26 nonillion sounds precise. It's meaningless. We can't mine 55 Cancri E, and diamond prices would collapse if we could. Precision doesn't equal accuracy. Green flag number 1. Quotes from uninvolved scientists. Good articles seek outside expert opinions. If everyone quoted is from the research team, skepticism is absent. Green flag number 2. Explains methodology. How do we know this? If an article explains the methods, it's treating you as intelligent. Green flag number 3. Discusses limitations. What don't we know yet? Acknowledging uncertainty is a sign of quality. Green flag number 4. Links to the actual paper. Lets you verify claims. If an article doesn't link to the source, ask why. The goal isn't cynicism. It's informed enthusiasm. Science is exciting because it's uncertain, iterative, and self-correcting. As of 2025, we've confirmed over 5,600 exoplanets. For most, we know. Mass, sometimes. Radius, if transiting. Orbital period. For a small fraction, we have atmospheric data, temperature estimates, rough composition models. For an even smaller fraction, detailed spectroscopy, weather patterns, surface conditions. The confidence spectrum. High confidence. Gas giants with thick atmospheres, easier to study. Medium confidence. Hot, rocky worlds close to stars, like 55 Cancri e. Low confidence. Earth-sized planets in habitable zones. Too faint, too far. When you see headlines like Earth-like planet discovered, ask, how Earth-like? What do we actually know? Often, the answer is rocky, in the habitable zone, maybe has water. That's very different from Earth 2.0. Why go through all this? Because how we talk about science shapes how people trust science. When Diamond Planet gets debunked, some people think scientists lied. They didn't. They made a model, then refined it. But if we present models as discoveries, refinement looks like failure. The truth is more powerful. Science is a process of getting less wrong. We make our best guesses with available data, then we test those guesses, then we update them. 55 Cancri e went from carbon-rich planet, possibly diamond, to magma ocean with volcanic atmosphere. Because we got better telescopes. In 10 years, with even better instruments, we might refine it further. That's not failure. That's progress. And it's far more interesting than a planet made of diamond. Here's what we actually know about 55 Cancri e. It's a world where the surface is molten, where rock vaporizes into the atmosphere, where volcanoes constantly reshape the landscape, where tidal forces from a nearby star generate so much heat that the planet glows like an ember, where a year lasts less than one Earth day. Is that less interesting than a diamond planet? No. It's weirder, more dynamic, more alien. And it's real, or at least it's our best current understanding of reality. We wanted 55 Cancri e to be made of diamond because diamonds are valuable, rare, beautiful. But science doesn't care what we want. It cares what's true. And the truth, that we live in a universe strange enough to have lava planets, diamond cores deep inside gas giants, and worlds we haven't even imagined yet, is better than any myth. This is Cosmic Canvas, where we explore the universe as it actually is, uncertain, iterative, and endlessly surprising. Until next time, read the paper, not the headline. Question the claims. And remember, getting less wrong is how we get it right.